All right. Well, hello. Welcome back. So, last video you should have watched, assuming you're watching this for chemistry, is talking about mass, volume, density, right? Some basics of matter, right? Very, very basic stuff. And now we're going to talk about, hey, what's this matter stuff made out of? And the spoiler alert is atoms, right? You probably heard of those before. So let's talk about them. Okay. And there's, start with basics. Basics are hopefully easy. So let's see how we do. Atomic structure, what atoms are made out of. Okay, you say, hey, matter is made of these things called atoms. Okay, and atoms are what we're interested in chemistry, of course. We want to know what they're made out of. We want to know how they behave. We want to know why gold is golden colored and very dense, and why silver is silver colored and less dense, right? And why neon is non-reactive and why hydrogen is very reactive, right? Like we want to know the properties of matter. We better understand what it's made out of and what those pieces are and what they mean, if it makes sense. Okay, so some basics. I just have this here as kind of reference. The word atom comes from the Greek word, I believe it's pronounced atomos, but I'm not Greek. So somebody who's Greek can comment angrily in the chat and say, no, that's not right. But hopefully that's right. It means indivisible because the idea of an atom is it's, in theory, the building block of matter, right? Nothing can be smaller. And we know that's not true. Okay, like you're like, what? Yeah, atoms can be broken down into smaller things. We can, of course, split atoms into smaller atoms. Okay, not that it's easy, but it's something we can do. Okay, and there are things even smaller than protons and neutrons and electrons. Okay, it gets even crazier. Okay, that's more of a physics thing though than chemistry, getting into quarks and gluons and muons and leptons and all sorts of fun particles in the standard model. But that's not this class. That's way above the scope of a high school class. Okay, all right. The idea is that atoms are the building block of matter. Again, it's not that it's like wrong, as in horribly wrong, but we now know it's not quite correct. Okay, atoms are not the smallest thing there is. Okay, all right. Continuing, the components of an atom, we got three what are called subatomic particles. These are things smaller than an atom. Sub means below; they're smaller, right? We have protons, we have neutrons, and we have electrons. Yay. Okay, so let's talk about each one in detail. Okay, here's a picture. This model, not that it's horrible, but yeah, I'm not really a fan of this, and we'll talk about why when we get to more about electrons. But basically, electrons do not just swing around on these little rings. That does not happen, but we'll talk about when we get to it. All right, protons. First and most important thing is they are positively charged. They have charge. And charge, if you're confused about what that is, you say, what do you mean by charge? It basically means magnetic. Okay, the concept here meaning like, if I have a north end of a magnet and another north end of a magnet, they do not want to be near each other. They repel. Like charges repel. They're magnetic. They don't want to be near the same charge. Okay, if I flip them both, now I have two negatives. Again, they don't want to be near each other. They repel. But if I flip one and leave the other one, right, then they attract because opposites attract. Okay, so that's what you should think of when you think of charge. How you get charge, why there's charge. These are great questions. I appreciate you asking those. Way above the scope of this class, okay? Not that it's impossible, but that's more of a physics question than it is a chemistry question, okay? There are times we'll talk in chemistry about how you can have charges get created by taking away electrons or adding electrons, right? But how you have charge in the first place, like why a proton has charge, that's not a simple answer to give for a high school class, okay? So, not that I'm against answering it, but I don't want to get too bogged down in some physics in this class, okay? Protons contribute to the mass of an atom, okay? Which means if I have more protons, the element, the atom I'm looking at gets heavier, okay? So gold has 79 protons, okay? It is way heavier per atom, way more massive than, say, hydrogen, which only has one proton, right? Generally speaking, if I go higher on the periodic table, the elements get light, and usually less dense for that matter. And if I go further down the periodic table, they tend to get heavier, more massive, typically more dense. Okay, so something to consider. All right. Protons are found in the nucleus of the atom. The nucleus is the dense center of the atom. Okay, when I say the dense center, I mean an atom is basically, you could picture it like a ball, like a sphere, right? Some kind of spherical shape. Okay, the nucleus is very tiny. Very, very, very small, found in the middle. Okay, and the rest of an atom is mostly empty space. Okay, that's most of an atom. And we'll see how we know that here in a couple seconds. Okay, the dense center of the atom. Okay, all the mass of an atom is found in the nucleus. Okay, protons define the identity of the atom, which basically means this: you count how many protons an element has, or how many an atom has. That tells you which element it is. There are 118 named elements. Okay, if you ask, are there more? Well, we don't really know. It's possible. They'd be very unstable, but it's possible. But right now we have seen 118 elements. Okay, and the number goes up to 118. If I have 118 protons, that is the element oganesson. Okay, that is the biggest element, exceptionally radioactive, doesn't exist for very long, it breaks apart very quickly. Okay, the smallest element is hydrogen with 1 proton. Okay, helium has 2 protons, lithium has 3 protons, beryllium has 4, boron 5, carbon 6, right? You don't have to memorize these, but you have to be aware that the number of protons always tells you which element it is. Okay, that's called the atomic number. We'll get to that in a couple seconds. Okay, again, example, 6 protons, gotta be carbon. Okay, hydrogen 1, helium 2, lithium 3, so on and so forth. Okay, only protons matter. I don't care how many neutrons it has, I don't care how many electrons it has, the protons matter. Okay? All right, next one is neutrons. Neutrons, by the name neutron, they are neutral. They have no charge, okay? But they do have mass. Technically, they're a little bit heavier, actually, than protons. Just a little bit, okay? At the high school level, even like early college, we tend to ignore this. We're kind of like, it's close enough, all right? They're both treated as 1 AMU. An AMU is an atomic mass unit. Okay, we treat them as 1 AMU, a piece. If you say, how many grams is that? Insanely small. Okay, so small, I mean, top of my head, it's, I think, in the picogram range, but I might be wrong, so don't quote me on that. It's been a while. We don't usually work with individual atoms and their mass, okay? That's not what we do in chemistry. At least I've never done that, okay? But in any case, very, very, very small, okay? Neutrons have mass. They're found in the nucleus as well. Nucleus, neutron kind of makes sense. You can change the number of neutrons, right? So earlier I said protons, if you change them, it's a different element, right? If I give gold another proton, it turns into mercury, if I remember correctly. Mercury, I think, is 80, okay? That's very different, right? Gold is gold. It's solid. It's pretty dense. Mercury is a liquid metal room temperature. Okay, that's very different, as you can imagine. Okay, so changing protons has dramatic changes. I could change the number of neutrons, and it really doesn't do that much to gold. Okay, I say that, and there are exceptions, but generally speaking, changing neutrons does not change the element or the element's properties. Okay, I can give gold more neutrons. It's still gold. It's still golden color. It might be slightly heavier, but it's still gold. Okay. If you're saying, what do you mean by some exceptions? If you give, for example, uranium, if you take away 3 neutrons, it turns into uranium-235, which is very fissile, which means it can undergo fission very easily because you've made something that is ready to go. That nucleus is ready to break. As soon as it hits neutron, turns into 236, it says, I'm done, and splits, and that's how you have a nuclear bomb, at least a fission bomb. But we're not there yet. That's going to come later when we talk about fission and fusion. Okay, for right now, you say neutrons don't really change much about the element. Okay, neutrons are like the glue that keeps the nucleus together. Okay, that's my analogy I often use is like you have this nucleus with all these protons. They don't want to be near each other, right? They're positively charged. They really don't want to be near each other. That said, there's a thing called the strong nuclear force that keeps them together. And we don't know why, okay? And if you're like, yes, we do, well, I'd like to hear the reason. I've never heard of a reason that's satisfied my curiosity. It's just a thing we establish. We say, hey, the protons stay together. Very strong force. We don't know why, okay? One thing I would say is that the neutrons basically are there to kind of like keep the nucleus together, okay? You put too much glue, it ruins it. You take glue away, it falls apart. There's like the right amount of glue, if that makes sense. And we'll talk about that when we get to isotopes, okay? If you change the number of neutrons, you have created what's called an isotope. Okay, an isotope is the same element, different number of neutrons, okay? Hopefully that makes sense. All right, last one is electrons. These are the most important ones in chemistry. They have negative charge. Because they're opposite to the protons, there's attraction, right? You might be tempted to say, well, shouldn't they just zip into the nucleus? That would make sense, but if that happened, that would be very bad. Okay, these electrons have velocity. They're going around the nucleus, and they are basically, think of it as like bees swarming around a nest. That's basically what the electrons are doing. Okay, they don't go in the nest though. If they do, it blows up. Don't let that happen. We don't want that. Okay. Electrons are outside the nucleus. As I said, they're kind of like bees swarming around the nest. They're located in what we call orbitals. Orbitals are not rings. Orbitals are not lines that they follow a path. They're basically like, imagine like a ball around the nucleus. That would be an s orbital, a spherical orbital, okay, hanging around it. If they're in a p orbital, they look like little dumbbells on the side, okay? We're not there yet, so if you're like, do I need to know this yet? No, but you should be aware they're in orbitals. For right now, we think of it as the electron cloud, okay? There's electrons somewhere around the nucleus, okay? Complicated. All right. As I said earlier, the vast majority of an atom is empty space. Okay, you could say it's the electron cloud. That's fine, but it's not like there's stuff. It's not like it's a cloud. Like, oh look, you can feel the cloud with your hand. No. It's empty space. Okay, and the electrons are found somewhere in that empty space. Okay, and again, we'll get to orbitals. It'll be a little bit more refined, but for right now, it's not the nucleus. Here's the nucleus. The rest of the atom is all around it. The electrons are somewhere in there. A good analogy that I've often heard of how big an atom is compared to its nucleus is if you took like a grain of rice and put it at the 50-yard line of a football field, think of it as that grain of rice is like the nucleus. The rest of the football field would be like the rest of the atom, mostly empty space. The nucleus is that tiny little center where all the mass is, okay? And the rest of it is empty space where electrons are somewhere zipping around, okay? For this level, we're going to say that electrons don't have mass. They do, okay? You go to college, please don't say, hey, that guy on YouTube lied to me. No, they have mass. It's just so small. It's like a 2,000th, if I recall, of a proton. It's such a tiny mass, we usually neglect it. We usually say it doesn't really make a difference, okay? And when I say this, I'm not just saying it as an opinion. I'm saying like when I was in college, we never really used the electron mass, okay? Obviously, if you're doing work where that could matter, then you might factor it in. But for like your first 2 years in chemistry, it probably won't make a difference at all. Okay? Be aware it does have mass, but we treat it as basically no mass. Okay? And the number of electrons, of course, can change. Just like neutrons, we can change electrons. We call these ions, and they're very important. Okay? Electrons are basically the most important thing in chemistry. I think I mentioned that before, but yeah, now that we're on the topic, they're very, very, very important. Okay? Most of chemistry is where are they? Where are they going? What happens if I change them? Why does this element want electrons? Why does this one not want electrons? And that explains a lot of behavior in chemistry. Okay? All right. How do we know all this? Now, these are videos that I have in my slides. You can take a look at them. If you're watching this on YouTube and you're like, I don't have your slides, what do you mean? This is the Rutherford gold foil experiment. Okay? What I'll show you, just so you can see, let me, I guess, maybe switch over here, maybe, is a PhET simulator, which is very, very, very useful. So for those who don't know, PhET is University of Colorado has simulators, and they're very, very, very nice. Okay, I think every science teacher in the world loves these things. They're great. Okay, I wish I had these when I was in high school. I don't remember seeing them. They might have existed. I don't think they did. Here's the point, though. I have my two atom models, the plum pudding and the Rutherford model. Okay, the plum pudding is what Rutherford, when he started the experiment, that's what they thought atoms were like, basically just a blob with electrons. Well, they didn't know they're electrons. Negatives and positives, interspaced. Okay. Rutherford did an experiment where he shot alpha particles through gold. Okay. And what happened is almost all the alpha particles went straight through it like it was nothing. Okay. They had a detector behind the gold foil. The alpha particles went right through it. And they're like, wow, that must mean most of an atom is empty space. That's the number one conclusion. Number two is this. If you look, right, this is like a zoom in. It's showing a very tiny size, right? 10 to the negative 10 meters. That is literally less than a billionth of a meter. Insanely small, okay? So if I were to turn on the alpha particle machine, in this case letting off alpha radiation, these purple little dots represent alpha particles, which for the record are helium nuclei. They're helium atoms without their electrons. So they're positively charged. They have a +2 charge. They're positive. This is important because if you notice, I'll turn the traces on so you can see it. You'll notice that when these alpha particles get close to the nucleus of one of these atoms, what happens? They scatter, right? They're getting closer and closer and closer, and because they're both positively charged, they want nothing to do with each other, so they bounce away from each other. Okay, the gold is solid; it can't move; it's just sitting there. So the alpha particles come in, and if they're going by the nucleus, and if they're far enough away, they just go, see you later. If they get close enough, they get close to the nucleus, and they basically deflect away. Okay, the experiment showed, again, two major things: atoms are mostly empty space, and that there's a dense, positively charged nucleus to an atom. Okay, and again, I can't remember what year. I don't even know if Rutherford gave it the name of proton, to be honest. But the idea is his experiment showed protons. If I remember correctly, it was his student Moseley, I think, was the one who gave it the name proton. But that doesn't really matter. Okay, so hopefully that makes sense. The other experiment that I'll mention is the cathode ray tube, or CRT. Okay, and I'll just show you, hopefully, probably a picture here. Yeah, this is fine. So if I were to look at this, right, the idea here, actually, you know what, let's get a maybe a real-life picture that might be prettier. Yeah, maybe this right here is good. Yeah, this is good. Okay, so you can see this green beam. Okay, the beam itself is colorless. This is a phosphorescent screen, so you can see it. It's like glow-in-the-dark, essentially. And what you're seeing here is electrons. You say, well, that's cool. How do we know that? Well, this is in a time where electricity was like a new thing. This experiment, I think, was 1906, if I remember correctly. It doesn't really matter. I'm not going to ask you about that, but just FYI. Trying to figure out what electricity is, right? Hey, this stuff that we're figuring out turns light bulbs on. What is it? How does it work? And basically what this guy named J.J. Thomson figured out was that this beam gets deflected by magnets. If you have the magnet end that's negative, it repels the beam. The beam gets pushed away, basically. Okay, so if you look over here, you can see it getting deflected. So the magnet, if it's negative, the beam is going this way, here comes your magnet. They're both negative. What does it do? It says, I don't want to be near that, right? It deflects away. If I flip the magnet, now it's positive, the beam says, ooh, and moves towards it, deflects towards it. Okay, so Thomson's like, hey, those particles must be negatively charged. Hey, we know an atom has to have charge neutral, or should be charge neutral. Hey, maybe these are the things in an atom that are negative. It's basically the logical process, okay? It's not like this took 5 seconds, by the way. It took you're talking about your results of your experiment, trying to figure it out. It's not like you just figured this out in 5 seconds, right? You get your experiment, you look at your data, you try to make sense of it, talk to other people, see what they say, okay? So that's how we figure this stuff out. And hopefully you say, oh, okay, interesting. And again, feel free to watch some videos on it. I have some here in my slides, but it is what it is, right? Here's a cool picture showing you the deflection, right? All right, so let's get back to the slides. I want to finish that so we can get you, hopefully keep this video relatively short. All right. Identity of atoms, this is basically what we talk about with protons. So if I were to look at an element and I say, what element is this? I just need to count protons. Okay, now you're not going to look at an atom, you're not going to pick it up with tweezers and go 1, 2, 3. They're too small, right? So what you would say is we would use our periodic table and we look at what's called the atomic number. The atomic number is simply the number of protons. That's what it always is, no questions asked. So if I were to say, hey, 56 protons, who's got it? I'm going to pull up my periodic table, and I'm going to say 56, where's 56? And thankfully, the periodic table is a beautiful thing. It has reason written all over it, okay? Meaning like everything about it makes sense. And if you're like, no, it doesn't, it's weird, keep watching my videos, it'll make more sense. For right now, why does it make sense? You say 56, where is it? Here's 1, here's 2, here's 3. Hey, they're going numerically. Interesting, right? Chronologically, I guess you could say, right? Or that's not the right word, but you know what I mean. Numerically getting bigger, least to greatest. 56, you're looking, okay, there's 46, 51. Oh, 56 right over here. Barium. Okay, barium has 56 protons. It has to have 56 protons. If it does not have 56 protons, it's not barium. If I take away a proton, it's cesium. If I give it an extra proton, now it's lanthanum. Okay, it changes the identity, and the identity is critical. Meaning, like, this is not like, oh, it goes from silver to slightly silver. Okay, if I took nitrogen and turned it into oxygen, you would know, because nitrogen would put a fire out. Oxygen would make the fire worse. If I took the oxygen you're breathing and turned it into fluorine, you'd be very unhappy, because your lungs would be, I don't want to say light on fire, but they would be very upset at you. Fluorine is very toxic. Okay, it would very badly burn you, very badly chemically burn your lungs. Okay, the point is, these changes are not minor. If I took fluorine and gave it a proton, guess what? It goes from super dangerous, super reactive to neon gas, which is completely innocuous, not dangerous at all. Okay, so this matters. The identity matters big time. All right, so 56 protons, you say, hey, that's barium. Okay, these are just practice ones. Like lithium's going to be 3. Okay, and again, if you're like, how do you know this? I have pretty good memory, but also these are pretty easy ones. Okay, lithium is 3. Tungsten's weird. It's W. The Germans named it. They called it Wolfram, so it's W. Okay, it's right here. Okay, and that has 74 protons. Neon, this is 10 protons, right? Nickel, I think, is 28. Hey, it is. Look at that. Good. Okay, and again, how do I get those? I just look at the periodic table. The number I'm looking at is that top number, and it's always an integer. It's always a whole number. It's never a decimal. We'll talk about this decimal here in a couple seconds. Okay, so looked at those examples. Great. Atomic mass is the other number on the periodic table. This is the number of protons plus the number of neutrons. Okay, so it's almost always a bigger number. Okay, the exception to that would be like hydrogen. Hydrogen's mass is 1. Hydrogen's atomic number is 1. Okay, there's a reason for that. It's not like it's random. Okay, it's because it only has 1 proton. There's no neutrons usually. That's the answer. But anyway. Okay, we basically treat neutrons as having the same mass as protons, as we said. So the number you see here is written as a decimal, and it's written in a unit called AMUs. It's a very non-creative name. Us scientists don't have the most creative mind sometimes. That's not true. Plenty of us do. I don't. I'm not very creative, but there's plenty that do. Okay. Point is AMUs, very boring name, atomic mass units. A proton is 1. A neutron is 1. Okay. 1 AMU. All right. And these units, we're only going to use these for individual atoms or individual molecules. We do not use this usually in chemistry. If I want to know, like I'm looking at this pen, I say how many atoms are in here. You might say, oh, is it like 1,000,000? Is it like 1,000,000,000? No, the number of atoms in this pen is probably somewhere in the neighborhood of like 10 to the 22nd, which is a big number. Okay, and I would not use AMUs for that. I would use grams. When you get to numbers that big, then AMUs start to turn into grams. Okay, we'll get to the mole later on. That'll make all sorts of sense. But for right now, individual atoms, we use AMUs, molecules, AMUs. Molecule just means atoms bonded together. Okay, so sulfur, if I look at sulfur on the periodic table, it has an atomic number of 16 protons, and it has a mass of 32.066 AMUs. You say, why is it a decimal? Simplest answer is because this is an average, specifically what's called a weighted average. Okay, a weighted average is basically a number where you're taking into account that, if I dug in the ground sulfur out of the ground, okay, I'm going to have, 30 grams of sulfur in my shovel, right? Let's just say. Most of that sulfur is going to have an atomic mass of 32. It's going to have 16 protons, 16 neutrons, right? 32 minus 16 is 16. Yay, 16 neutrons. But there are some sulfur atoms, not a lot, but some, that are what is called sulfur 33. Why is it called that? Because it has 1 extra neutron. Okay, instead of being sulfur 32, it's sulfur 33. Okay, you could find sulfur that is sulfur 31, which is 1 less neutron. You can find sulfur that's sulfur 34, 2 extra neutrons. But when you take the average, specifically the weighted average, which means you're taking into account the percentages, like how often do we find sulfur 32, how often do we find sulfur 31, and so on and so forth, a weighted average tells me what the usual suspect is. In this case, it's very close to 32 because the vast majority of sulfur you find is going to be sulfur 32. But notice, for example, like thallium, right, TL over here, notice 204.383. So the average mass is around 204, right? But you're going to find some that's higher than that, probably 205, some 206. Look at gold, 196.967, very close to 197, but that means there's a decent amount of gold that's not 197, maybe 196, 194, and so on and so forth. Okay, we'll talk about that calculation in another video. Okay, not that it's that hard, but it's a little bit more. I don't want to keep this video too much longer. Okay, again, talked about this idea of a weighted average. Okay, so hydrogen is a great example. Hydrogen's mass is 1.008, very close to 1, because like 99% of hydrogen is hydrogen 1. There is a very small percentage that is hydrogen 2. It has 1 proton, 1 neutron. Okay, and then an even smaller percentage that is hydrogen 3. Okay, what's called tritium, and that's insanely rare. Okay, but notice copper, 63.546. It's kind of like between 63 and 64. which means you have a lot of copper that's 63 and a lot of copper that's 64. I shouldn't say it's guaranteed to be that, but that's likely what it is. Okay, we could check for sure, but pretty sure that that's that specific example. I'm pretty sure 63 and 64 are the main constituents. Okay, and again, doing the math, you would say maybe copper 64, you would take 64, you would subtract 29. Why 29? That's the atomic number, 29 protons, and you get 35 neutrons. If we look at this with isotopes, how does it work? You give the name of an isotope by saying the element and the mass. So if I say lithium-7, I would say that out loud, lithium-7. That would have 3 protons. It's lithium. It has to have 3 protons. 7 minus 3 is 4. 3 protons, 4 neutrons, a mass of 7. If I had lithium-8, an isotope of lithium, right, this has 1 extra neutron. How do I know that? 8 minus 3 is 5. Okay, so a mass of 8. All right. And then with electrons, this is very simple. To start out at the very least, you just take the atomic number. That's the number of electrons. And it makes sense because if you have 5 negatives or 5 positives in boron, we should have 5 negatives, right? 5 protons, 5 electrons cancel out, right? But you can change it, okay, right? We talked about this. You can add electrons, you can take away electrons, okay? So if it's an ion, again, I say more on this later because we're not hammering on that right now. But for right now, you say, hey, generally, the number of protons equals the number of electrons, unless it's an ion, which we'll get into. Okay? This idea of charge balance is a good thing. You say, why? The universe does not like concentrations of energy, is the short answer. Okay, what's called entropy. Okay, so carbon 12, 6 protons, 6 neutrons. How many electrons? 6. How do I know that? It's got 6 protons. It should have 6 negatives. Okay? All right, and phases of matter is where we're going to end the video here. So see you in the next video.